So let me talk to you a little bit about some of the work that we're doing in my area or the digital side. This is really, the key thing is all of these are flows and technologies which are used to be able to uh, design build chips. Some of these are some examples. Imagination is a company in UK for the people that aren't familiar with it. It does GPUs, uses Cadence Design Flow. We actually also have a machine learning flow, which we've been working closely with Samsung to optimize their advanced nodes. And Renaissance, the key automotive manufacturers are also using our machine learning digital flow. Using these machine learning flows, you can see that Samsung was able to get to, better PPA, about 8%, and Renaissance, they saw, about 15% lower power and better performance. So this is really, in terms of what chips are having, you have layout, netlist, synthesis, and place and route. As with it, as the compute power exists, you get larger and larger designs and more complex designs, and the time to market is ever shrinking. There's a huge incentive for people to get their chips through. So the question is, what's next? So we did actually introduce earlier this year Cerebrus, which is our machine learning tool. It's basically automates the design. So with it, if you use some of the Cadence tools right now, you do try different options. You see what your PPA, your power, performance, and area is. And then you actually try different options. You look at the results and you try to tweak and change different options. So what we've done instead is actually have a process where Cerebrus, which actually has machine learning on the outside. So basically it can automate, it looks at the results, it knows what needs to be done or tried next. It can look at the data set that is generated, and it can actually delivers 10x better productivity and up to 20% better power performance and area. We do use this within our whole system, so we can run this. And this is actually, as I showed you before, we have multiple customers that are currently using it and see good results from here. This is also uses, one of the key things is, in today's computer environment, cloud is critical. They actually have a way of, so in terms of making sure it's on the cloud is critical as well. So, this is a traditional flow where people would run through the flow, get out results, and there was an expert, and then you would basically iterate with the different options, constraints, and library options, and it required a lot of engineering resources. And with Cerebrus, we can actually go through. We have the options, we have the reinforced learning, and it does design analytics. So this way, you actually can get to the best results with shorter schedules and fewer people. So we have, I think, very effectively applied machine learning to our flow. We are actually working and improving this over time, moving this to other parts of the flow. There's other things that you can do with machine learning. I think machine learning really opens up a whole nother dimension. We can prove that many of the problems that we face in digital design are provably not solvable. So having a machine learning flow can enable much better results. So here are some results we've had, overall manual effort. And you can see actually, in addition to, within 10 days, we can get an improved flow with much better performance. Today's results too, you can actually see some people are more concerned about timing, and power is also a key metric for right now. This is also, you can also use machine learning. Another thing you do in machine learning, not just in terms of looking for the best performance and power, but also to find the best floor plan. So what you would do in terms of the design process is you first actually have to say for these huge chips, which have 10 million, 100 million gates. You actually break it up into different pieces, into blocks. And we can actually use machine learning to be able to break this into manageable size blocks. A typical block size that you'll go through will be about 5 to within 10 million. So if for designs which are easily 100 million or so, you actually do have to break it up, and this is where you create the floor plan. So you can actually use this machine learning for this. With these optimized, with being able to do this, you can explore more options, and this actually can significantly improve the performance, because depending on how you break it up and how you place it, you will get much different results. And on a manual, someone doing it manually is actually going to have a difficult time exploring all those different options. So let me talk to you a little bit about what are some of the tools and some of the technologies which we have within our design flow. One is which we would start. Many people start with this flow is high-level synthesis. Typically, in a typical design environment, you would write VHDL or Verilog. That is a slightly lower level and tells you, what are all your registers, what are all your pipelines. We also have technology which can allow you to write in System C. This is actually a specification language which can be easily simulated. It simulates much faster than RTL, and it does not do all the pipelining and all of those details. This actually allows you to, schedule operations, pipeline, do all of these other things. And what you can do is actually it's a much faster, allows you to get a better design with a smaller, with a much shorter amount of runtime. Also, in terms of verification, the fact that when you have to actually do verification at the RTL level is much slower than at the System C level. So we are seeing key customers, Intel, Qualcomm, Sony, AMD. Many of these customers are actually moving to this. We call it high-level synthesis. Right now, we are one of the only two EDA vendors which have this. So I think this is something where you feed in System C, and then you actually feed in the constraints, and then will actually generate the RTL that you can use for the rest of the flow. We also can explore many options. So we are working on solutions with Cerebrus to improve this as well. Another thing that we also do is the most important metric that many people use today is power analysis, and power timing is critical to make sure it's fast enough. But what we're seeing now is, especially with all of the battery powered operations, power is extremely critical. So we do have our solution is called Joules, and that actually allows you to do power analysis. It is the engine for analysis within all of our optimization tools. This actually is used throughout the flow, and it does work where you can actually automatically, as I said, some of these keys to be able to link between simulation. Excellium and Palladium are part of our simulation, some of our simulation offerings. You can take test benches out, have it in a compressed way, and this can tell you what your real power is. Depending on what the vectors are that you use, that determines what your power is. So using some of these things, especially since they're used within Joules, Genus, and Innovis. Genus is basically this is a synthesis and the place and route tools. Joules is the engine behind there, can allow you to optimize and get a better power reduction. So we have both the capability to estimate what the power is very early on when you're doing analysis, as well as it's the driving engine within our optimization tools to be able to enable you better power. Greg mentioned also, another product that I'm responsible for is Modus. This is our test solution, which enables both design for DFT is designed for testability. Design for testability is all of the structures that you need in order to be able to test and get the high pattern coverage. As you can think, actually one of our customers is actually a big electric automotive manufacturers. They need to make sure that they have all of the structures to be able to test. So some things are, you think of scan chains where you have to make sure all of the registers are correct, and they can take ones and zeros and move them along. You also need to make sure you have things like, memory BIST basically allow you to test your memory and system. Logic BIST allow you to test your logic and system. And we actually are seeing, especially with automotive and aging and other things, that we really have to have more and more of these test logics that are inside. ATPG is the tool which actually generates the patterns which you have to have, be able to test your patterns at a 99+%, and then also diagnostics, be able to find out if you do have a problem, where does it come from. Why Cadence has a unique place here is that because we do have a very strong digital offering, we can actually ensure that our performance for all of this DFT logic gets the best results. So with it, we actually can get because we're integrated within the whole implementation system, we get the best power, performance, and area. So we have been talking to another customer, one of the big automotive customers, and they found that they didn't get their pattern count. They had to insert some test points, some extra registers at a later stage. And when they did that, they would circle, and they would have trouble meeting their power and their timing goals. So with the fact that we're integrated within the whole system, we can achieve their power, timing, and area goals with still being able to add this. We do have a full solution with, scan. We have compressions to allow you to not put in all of the pins. You can actually just use a small number of pins, and we can actually then use this to dry up all the scan chains. And we also do, in terms of ensuring that just the raw pattern count, we do actually have a differentiated solution. You actually have to be able to test for those different fault models, which can cause problems with your design. So within Modus, we do have a unique way of putting it all together. You can see it all in one place. We also do have another thing I'm also responsible for is Conformal. Conformal is our verification technology. It is, number one in the industry too. It actually has multiple different pieces. This is actually required every time you go out to design. You have to make sure that your design is correct. So nobody, we're working with key customers, nobody can tape out their designs without going through formal verification. Otherwise, you risk this. On top of that, they will do some simulation, but some simulation also is really simulations gated by the number of patterns that you can apply, whereas formal verification will ensure that your logic is correct. So therefore, you don't have to do test vectors, and then you have to get independent verification. So this way, we do work very closely with both the Cadence full flow, and we do also support the other tools vendors for it. With it, in today's designs, low power technology is critical. People do things, everybody does level shifters, shuts off blocks. You have to do isolation cells. You have to, and those can actually be arbitrarily complex. Whole language UPF, which specifies how to do this. The synthesis tool will insert it, place route will insert it, and this way Conformal can also validate that it's correct. We also do another thing that also people are doing now too is called ECO, engineering change order, is what it means. And generally, if you had something which had a problem at the end of the flow, you could actually go through and measure and just change a small portion of the design. You basically say, if I want to swap out this gate for this other gate, you generally do it on like 100 or 1,000 gates. What we're seeing now is because of the excessive turnaround time, some of our key customers are actually freezing the design cycle early, and instead are using ECO to be able to change and basically say the RTO is frozen at a certain point, but instead I will go into place and route. If I see a problem there, either for performance or functionality, they can go and just use ECO, which effectively finds the smallest piece of design to swap out, and then it actually can improve the time for a designer to be able to go through the whole process. We also have functionality which also validates the timing constraints and the clocks. So these are all of the different verification technologies which we have, and all of those, I think, in today's techniques are required. Another thing actually, which is I think what Cadence is also known for, is place and route. They are the market leader for advanced nodes. This actually does have, the reason why is because we have the best power, performance, and area. The different pieces I'll talk about very quickly are placement, optimization, clock, and routing. And in today's designs, you also have to have a hierarchical flow. Designs are just much too big to be able to enable that. And we also have ensuring we go through when we have the front end and sign off, you have to make sure that whatever you're optimizing to has to be the right timing and area. And we do, this is an area of its continuous innovation. We do work very closely with all the foundries to be able to ensure we can get all new technologies. So as they're coming out, they have to work with us. There's new technology required to support them in order to understand and get the best performance. We have continuous improvement there, as well as with the larger design size. So we're continually have, I think, many more ideas and work to be doing for how we can continuously improve this. So let me just very briefly talk about some of the different pieces. One of the first places you work through is just to make sure you have to do placement. You have to do placement. It's a problem. It's a computational problem that needs to be solved with this numerical placer, which has multiple objectives. We have to be able to place not just standard cells, but also memory. You have to be aware of not just timing, but also IR drop, and be able to support some of the advanced nodes. The advanced nodes also do require placement rules. So these things, especially where the pin access becomes more challenging. We also have to make sure once you do that, the logic optimization has many different paces. We do use engines all the way through to make sure that as we go through different stages, you can optimize this. In terms of the different pieces, you have to make sure, we obviously do a lot with power. And other challenges with smaller designs is that you'll have wires crossing. And with this, then if you have too much congestion, too many wires crossing will cause problems based on crosstalk and just not being able to route the design. And we do several different optimizations to be able to enable this. Some of it, going back to the logical level, you can actually use things like clocks and basically delay a clock from one register and other ones, and also do things in terms of how you do routing and how you do the design and where you're going to place on the layers. You also there's a lot of work to be done on clock trees. Clock trees do become arbitrarily complex. People know the general clock tree. Useful skew is an optimization technique I just mentioned before, where you can use this to make your design meet timing. But there's now other types of different clock trees you can do, H-tree or mesh, where different customers are using this, and you can have different advantages for enabling this. And then finally, you'll go through routing. With it, routing is a complex problem, so it has to be distributed and understand. There's an incredible amount of routing rules to be taken into account too for all the different pieces. We are using, not just in CMOS, we are looking at some of the other technologies which are more advanced too. Those also require new advanced nodes. And of course, you have to be able to understand timing, power, and do basically some of the bus planning. And then finally, as I mentioned before, all the optimization we needs to be actually understand. It's key that we have these sign-off engines. So once you get through a design, you have to actually go through sign-off, which is Tempest is our sign-off engine, sign-off timing engine. Tempest PI does the IR drop, and you have to do the extraction. And also this is the LVS DRC, the physical DRC. And all of these engines are actually used to drive the optimization for the end of us. This is actually key because you need to be able to sign off, but you need to make sure as you optimize that you don't loop. If you try to fix something, you go back to later and find out that there's a different problem. So there's obviously a lot of work to be done in all these for different effects, different, as we see now, aging is a new thing we need to focus on. So we're doing work on Tempest on this side. So overall, as I kind of introduced, these are our core metrics, core principles, best in class, parallelization, and full flow. And these are the different parts of the flow that need to be worked together in order to be successful.